So, have you guys ever, everybody's seen neon signs, right? So if atoms absorb a lot of heat, or if they absorb a lot of, let's say, voltage, they can end up absorbing that energy, right? And then releasing it in the form of light. So where do we see that? Neon signs. What is a neon sign? It's basically a gas tube that has, you know, let's say a noble gas, an element, and then you have voltage of electricity run through it, and it excites the electrons in the atom. So, right, when we talked about this before, I'll do lithium. Remember we had lithium, right? And lithium has a nucleus. I think it has three, right? It has 3 protons, 4 neutrons. That's the nucleus. And then it has 3 electrons. So in the first, right? In the first shell, you have 2 electrons. And then in the second shell, do you guys remember us doing this to explain ionic compounds?
Yes.
And then the second shell, we have 1 electron.
1.
Right? Well, if energy comes in the form of light and it excites an electron, what goes up must
come down.
Come down. And it must drop back down. Well, when it drops back down, right, it absorbed energy. So a neon sign absorbs energy in the form of voltage. When it drops back down, the electron, it's got to release the energy. So how does it release it? It emits light. So as the electron is falling down, it's releasing light. So in lab, a lot of times you have these tubes of elements, these discharge tubes, and you could look at the light that's being released. And more importantly, you can take a spectroscope that has a slit, and the slit will narrow that light into a prism. And what do prisms do?
Prisms bend the light.
Prisms bend the light. That's exactly correct. That's how we see rainbows, right? The water droplets act like little prisms, bend the light. If it's white light, we see a rainbow. However, with atoms, it's different. How is it different? Well, we get what's called an atomic emission spectra. So we can take, let's say, a hydrogen lamp, put some voltage in it, some energy, then take the light that it emits, narrow that beam of light through a slit, and bend it through a prism. But if you look at this emission spectrum of hydrogen, which they put it right here, how is it different than white light? How is this diffracted spectrum different than the white light?
It does not show all of the colors.
It's not continuous. So it's a discontinuous spectrum. White light has all the colors. It's continuous. Why? Because it has all amounts of energy. The element is not continuous. It has very specific lines. And this is where Bohr theorized that these very discrete lines represent a very specific amount of energy.
Mm.
And in fact, these line emission spectra are like the fingerprints of our elements. Every element has a different line spectra. So what does the atomic line spectra tell us? What did Bohr kind of use this line spectra to deduce and formulate some hypotheses and develop theories. So the individual lines were key to Bohr's atomic model. So we actually introduced Bohr's atomic model before. I think that was chapter 4 when we were talking about atomic theory, again with Dalton's atomic theory, Thomson's plum pudding model, and Rutherford's nuclear model with the gold foil experiment. So now we're getting to Bohr. So Bohr used his theory that the movement of electrons were the reason for atoms emitting light. So when electrons absorb energy and then when they drop back down, they emitted light. But again, why discrete lines? Why only specific colors? Bohr reasoned that electrons were only allowed to have a certain amount of energy. They couldn't have any energy. It was all or nothing, right? It wasn't continuous. So it was really strange. It's like someone telling you, you're only allowed to have a certain amount of money, right? So Bohr came up with the concept of orbits. So the Bohr model is an orbit model. So when you look at atoms, you have your dense nucleus, okay? And what do you have in your nucleus?
Protons.
Protons and neutrons. That's right. The protons and neutrons are in your dense nucleus. And what's outside of that? We figured that out with Rutherford's gold foil experiment. What's outside of the nucleus?
Electrons.
Electrons. We did this, I think, in like week 3. You can even look back at your notes. I made a table of the subatomic particles, their charges, their masses, and their location. So, but Bohr, he didn't say they were just outside, okay? He was a little more specific, and he used the emission spectra to calculate the energy. And what he came up with is the lines represented very specific orbits. And the orbits represent distances of where the electrons are from the nucleus. So the first orbit, they call it the principal quantum number. We'll make it easy. We'll call it the energy level. Okay, and you guys might remember when I would refer to the periodic table, I would say the first period, the first row is energy level 1. The second row, the second period would be energy level 2. The third period, and then I would draw those circles when we talked about ions. Well, that's the Bohr model. The first energy level 1, is the energy level closest to the nucleus. And because it's the smallest energy level, it can only fit 2 electrons. So 2 electrons try to get in there and fit, okay? When that orbit is filled, the next set of electrons have to go to the next orbit. And that next orbit would be energy level 2 or orbit 2. And once that gets filled, what happens? Where does the next set of electrons have to go?
The next orbit.
The next orbit. So orbit 3, orbit 4, orbit. So as I have more electrons, what happens to the number of orbits?
It increases.
It increases. So as I have more electrons and I have more orbits, what happens to the size of the atom?
It gets bigger.
Exactly. Does anyone remember what we call that outer orbit for an atom?
The valence
The
orbit.
valence shell. That's where the electrons are being exchanged in reactions. So we just talked about the activation energy in reactions that's required for a reaction to take place. Right after break bonds and make new ones. Where am I breaking the bonds?
In the valence shell.
In the valence shell. So now we're really getting into the meat and potatoes of all this. So the bond energies, the electron orbits in the Bohr models, they're like rings on a ladder, right? So you can't have your foot, it's going to be a very, you can't have your foot, that's a really bad shoe, in between the rungs of a ladder. You have to be on a rung, right? Or on another one. You can't be in between. So you're either on one rung or the other. You can't be in, there's no in between. And that's why those lines are very discrete and distinct. And they're not continuous like white light. So you can stand on one step or the other, but never in between. So each orbit in the Bohr model has a specific energy, and we're going to call that the quantum number. I was referring to it all along as the principal energy level, which we were calling period or rows. So that quantum number is it. And if you look at your periodic table, along the rows, you'll see the numbers 1, 2, 3, 4. That's n equals 1, n equals 2, n equals 3. So when an electron moves to a higher orbit, it must absorb energy. When it moves back down, it has to release that energy, right? Law of conservation of energy. I can't create or destroy it. I can only transform it. If I absorb it, I can then release it. So by studying light, we understand the movement of electrons between the orbits. So if energy is absorbed, so if energy comes in, they basically, they're showing this as a wavelength of light, comes in, right? The electron might get, it's called excited. So when energy is absorbed, electrons move up, that's called an excited state. Okay? When electrons drop down, a lot of times it's referred to the ground state, but when they drop down, when they go back down, this is referred to as relaxation. But as they drop back down, they have to release the energy, and they release it in the form of light emission. So energy is absorbed, electrons are excited. When the electron drops back down in a relaxation, it releases energy in the form of light, and it's called an emission.